Good day, everyone. I'm going to talk to you about time value of money. There are two parts. Today, I'm going to talk about part 1 and only cover part 2 next week. This is a long topic. We'll only cover half of the topics today, those in orange text. We'll look at the rest of the topics in blue text next week. The primary focus of today's and next week's lecture is to explain time value of money calculations and to illustrate economic equivalence. The term capital refers to wealth in the form of money or property that can be used to produce more wealth. Majority of engineering economic studies involve the commitment of capital for an extended period of time, so the effect of money must be considered. In this regard, it is recognized that a dollar today is worth more than a dollar 1 or more years from now, because of the interest or profit it can earn. Therefore, money has a time value. The riskiest thing a person can do with money is nothing. Money has value, and if money remains uninvested, the value is lost. Money changes in value not only because of interest rates, inflations, or deflations, as well as currency exchange rates, also cause money to change in value. Why do we consider return to capital? There are several fundamental reasons why return to capital in the form of interest and profit is an essential ingredient of engineering economic studies. Interest and profit pay the providers of capital for foregoing its use during the time the capital is being used. For example, you invest your capital to get the incentive so that you can accumulate capitals by saving. What you actually did is postponing immediate consumptions of your money in favor of creating wealth in the future. Interest and profit are payments for the risk the investor takes in letting another person or organizations to use his or her capital. In typical situations, investors must decide whether the expected return on their capital is sufficient to justify buying into a proposed project or venture. If capital is invested in a project, investors would expect, as a minimum, to receive a return at least equal to the amount they have sacrificed by not using it in some other available opportunity of comparable risk. This interest or profit available from an alternative investment is the opportunity cost of using capital in the proposed undertaking. Any project or venture must provide a sufficient return to be financially attractive to the supplier of money or property. In summary, whenever capital is required in engineering and other business or projects and ventures, it is essential that proper considerations be given to its cost, which means the time value. The remainder of this lecture deals with time value of money principles, which are vital to the proper evaluations of engineering projects that form the foundations of a firm's competitiveness, and hence to its very survival. Let's take a look at what is simple interest. When the total interest earned or charged is linearly proportional to the initial amount of the loan or principal, the interest rate, and the number of interest periods for which the principal is committed, the interest and interest rate are said to be simple. A simple interest is actually not used frequently in modern commercial practice. When simple interest is applicable, the total interest, denoted as I, earned or paid can be computed using this formula. I is equals to the product of P, N, and I. P is the principal amount lent or borrowed. N is the number of interest periods, for example, years, months, days, and etc. And I is the interest rate per interest period. The total amount repaid at the end of n interest periods is the summations of principal and the interest. This is a simple calculation example. If $5,000 were loaned for 5 years at a simple interest rate of 7% per year, what would be the interest earned? The interest earned can be calculated using this simple interest formula, I equals to P and I. And the principal P is $5,000, the period end is 5 years, and the interest rate I is 7%. Substitute these informations into the formula, we get the interest earned equals to $1,750. So the total amount owed at the end of 5 years would be the original amount of principal plus the total interest found above. Okay, this gives the total amount owed equals to $6,750. Now we look at a different interest known as compound interest. Whenever the interest charged for any interest period, for example a year, is based on the remaining principal amount plus any accumulated interest charges up to the beginning of that period, the interest is said to be compound. The effect of compounding of interest can be seen in this table. For $1,000 loan for 3 periods at an interest rate of 10% compounded each period. The amount owed at the beginning of period 1 is $1,000, and the amount of interest for period 1 is 10% of this $1,000, which is $100. Okay, this leads to amount owed at the beginning of period 1 equals to $1,100, which is by summing these two amounts. Okay, in period 2, the total amount owed at the end of period 1 is brought forward to the beginning of period 2, and this amount is used to calculate the interest for period 2, which is equals to $110. In other words, the interest accumulated in period 1 is used in the calculations of interest for period 2. Okay, similarly, the amount owed at the end of period 2 is brought forward to the beginning of period 3, and this amount is used in the calculations of interest for period 3. As you can see, the total interest is increasing from period 1 to period 3. Okay, this is different from simple interest, whereby the interest amount is fixed for each period. Okay, because of the compounding effect, a total of $1,331 would be due for repayment at the end of the third period. Okay, this amount is higher than the amount due for repayment if simple interest is used, which is $1,300. This is the plot of the amount owed as a function of the end of interest period for previous example to compare simple interest against compound interest. We can see that the amount owed is increasing faster with compound interest as compared to simple interest, which is linear. The difference is due to the effect of compounding, which is essentially the calculations of interest on previously earned interest. This difference will be much greater for larger amount of money, higher interest rates, and greater numbers of interest periods. Simple interest does consider the time value of money, but does not involve compounding of interest. Compound interest is much more common in practice than simple interest, and is used in personal and professional financial transactions. As you have learned in Lecture 1, alternatives should be compared when they produce similar results, serve the same purpose, or accomplish the same function. How can alternatives for providing the same service or accomplishing the same functions be compared when interest is involved over extended periods of time? We can use economic equivalence. Economic equivalence allows us to compare alternatives on a common basis. To carry out a comparison of alternatives, each alternative can be reduced to an equivalent basis that is dependent on the interest rate, the amount of money involved, and the timing of monetary receipts or expenses. Okay, using these elements, we can move cash flows so that we can compare them at particular points in time. This is an example to better understand the mechanics of interest and to explain the concept of equivalence. Okay, suppose you have a $17,000 balance on your credit card. Okay, this has got to stop, you say to yourself. So you decide to repay the $17,000 debt in 4 months. An unpaid credit card balance at the beginning of a month will be charged interest at a rate of 1% by your credit card company. For these situations, you have selected 3 plans to repay the $17,000 principal plus interest owed. The 3 plans for the repayment of $17,000 in 4 months are illustrated here. We will demonstrate that they are equivalent in terms of the interest rate is 1% per month on the unpaid balance of principal. Beginning from first column, we have period of repayment in month. Interest accrued at beginning of month. Interest accrued for month, which is obtained by multiplying the interest rate of 1% with the value in column 2. Total money owed at end of month, which is by summing values in column 2 and 3. Principal payment and total end of month payment of cash flows, which is obtained by summing values at column 3 and 5. Let's take a look at plan 1. Plan 1 is to pay interest due at end of each month and principal at end of 4th month. The monthly payments of interest is $170, and the final payment includes the principal plus the last interest payment. Because interest does not accumulate in plan 1, compounding of interest is not present in this situation. We can see that the interest charges for each month is calculated based on the principal. Altogether, there are $68,000 months of borrowing and $680 of total interest. Therefore, the monthly interest rate is $680 divided by $68,000 months times 100% is equals to 1%. Plan 2 is about paying off the debt in 4 equal end-of-month installments. The end-of-month installments is $4,357.10 per month, which include both the interest and partial repayment of principal in each month. We can observe that the interest being charged at each month is based on the remaining amount of principal owed at each month. For example, in the second month, the remaining amount of principal is $12,812.90. This is obtained by subtracting the principal payment in the first month, which is $4,187.10, from the initial debt of $17,000. The same calculations can be applied to get the remaining principal in subsequent month. The $17,000 principal is completely repaid over the 4 months period. You can see that the monthly interest rate is given by dividing the total interest, which is $427.10, by $42,709.5 months of borrowing times 100% to get 1%. There are fewer dollar months of borrowing in Plan 2 as compared with Plan 1 because principal is being repaid every month and the total amount of interest paid is less. In Plan 3, no interest and no principals are repaid in the first 3 months. Then at the end of the 4th month, a single lump sum amount of $17,690.27 is repaid. This includes the original principal of $17,000 and the accumulated compounded interest of $690.27. The dollar months of borrowing is very large for Plan 3, which is equals to $69,026.8 months, because none of the principal and the accumulated interest is repaid until the end of the fourth month. Again, the monthly interest rate is equals to 1%. These are the notations used in formulas for compound interest calculations. I is the effective interest rate per interest period. N is the number of compounding interest period. It can be days, weeks, months, years, and etc. P is the present sum of money, or the equivalent value of one or more cash flows at a reference point in the present. F is the future sum of money, or the equivalent value of one or more cash flows at a reference point in the future. And finally, A is the end of period cash flows in a uniform series, continuing for a specified number of periods, starting at the end of the first period and continuing through the last. The use of cash flow diagrams is strongly recommended for situations in which the analyst needs to clarify or visualize what is involved when flows of cash occurs at various times. In addition, viewpoint is an essential feature of cash flow diagrams. The difference between the total cash inflows and the total cash outflows for a specified period of time is the net cash flows for that period. The cash flows are important in engineering economy because cash flows form the basis for evaluating alternatives. This is a cash flow diagram for Plan 3 of previous example on the repayment of credit card balance. Let's look at the cash flow diagram in detail here. The cash flow diagram is drawn based on the cash flow information provided by this table, which we have looked at earlier. This cash flow diagram is drawn from the credit card company's viewpoint. The interest period is presented in months. At the beginning of the first month, a cash outflow of $17,000 occurs in the credit card company. This cash outflow is assigned as a present sum since it occurs at time 0, which is the start of the interest period. At the end of the fourth month, a repayment of $17,619.27 is received by the company. This is considered a cash inflow, and since it occurs at the end of the interest period, it is assigned as a future sum. The interest rate is 1% per month, applied across the entire interest period. This is a cash flow diagram for Plan 2. This diagram is still drawn from the credit card company's viewpoint. As compared to the previous cash flow diagram, the future sum is replaced with the annuity which occurs at the end of each month. From both diagrams, you may have observed that cash flow diagrams employ several conventions. The horizontal line is a time scale, with progressions of time moving from left to right. The period labels can be applied to intervals of time. The end of one period coincides with the beginning of the next period. The arrows signify cash flows and are placed at the end of the period. Downward arrows represent expenses or the negative cash flows or cash outflows. The upward arrows represent receipts or the positive cash flows or cash inflows. The cash flow diagram is dependent on the point of view. And this diagram shows the cash flows as seen by the lender or the credit card company. If the directions of all arrows had been reversed, the problem would have been diagrammed from the borrower's viewpoint. Let's look at one example on cash flow diagramming. Before evaluating the economic merits of a proposed investment, the XYZ corporations insist that X engineers develop a cash flow diagram of the proposal. An investment of $10,000 can be made that will produce uniform annual revenue of $5,310 for 5 years, and then have a market or recovery value of $2,000 at the end of year 5. Annual expenses will be $3,000 at the end of each year for operating and maintaining the project. Draw a cash flow diagram for the 5-year life of the project. Use a corporation's viewpoint. Here shows the cash flow diagram drawn based on the information given. The labels for timescale is given as end of year. The initial investment of $10,000 and the annual expenses of $3,000 are cash outflows. That's why they are drawn and indicated by downwards arrows. The annual revenue of $5,310 and the market value of $2,000 at the end of year 5 are cash inflows, and they are indicated by upward arrows. The locations of the arrows are simply the time when the cash flows occur. Now we'll look at how we can relate present and future equivalent values of single cash flows. Figure here shows a cash flow diagram involving a present equivalent value P, which is also known as the present sum, a future equivalent value F, which is also known as a future sum. These sums are separated by M periods, with interest rate per period equals to I. The dark solid arrow here is used to indicate the quantity that is given, and the dash arrow here is used to indicate the quantity to be determined. In engineering economy analysis, you could face different tasks. For example, you could be asked to find F when given P, or to find P when given F, or to find the interest rate given P, F, and N. We can apply compound interest formula to move cash flows along the cash flow diagram. Using the standard notations, we find that a present amount P can grow into a future amount F in M periods at interest rate I according to this formula, whereby 1 plus I to the power of n is the interest factor. In a similar way, we can find P given F by using this formula, which is formed by inverting the formula above. How do we get this formula for future sum? By the end of one period, we'll get the amount P plus PI, whereby P is the principal and PI is the total interest earned from the principal. This can be simplified as the multiplications of P with 1 plus I. By the end of 2 periods, the amount will grow into the multiplications of P with 1 plus I to the power of 2. This is obtained by simply bringing forward the amount all at the end of period 1 to period 2 and treating it as the amount all at the beginning of period 2 and calculate the interest charge on this amount. Similarly, by the end of 3 periods, the amount will become the multiplications of P with 1 plus I to the power of 3. And eventually, by the end of n periods, the amount will be the product of P and 1 plus I to the power of n. Let's have a look at one example. Future equivalent of a present sum. Suppose that you borrow $8,000 now, promising to repay the loan principal plus the accumulated interest in 4 years at interest rate I equals to 10% per year. How much would you repay at the end of 4 years? This is the solutions. By using the formula, the answer is straightforward, which is $11,713. We can also break down the solutions into the number of years we owe the money to visualize how much interest is being charged each year. Column 2 shows the principal and the amount owed at the start of the year. Column 3 shows the amount of interest owed for each year, which is 10% of the amount in column 2. Column 4 shows the principal plus the interest owed at end of each year. And the last column shows the total end of year payment. Since no repayment is done end of each year except at year 4, the interest is compounded over the first 3 years. It is common to use standard notations or functional symbol for interest factors. These interest factors can be written in this functional form, which is also known as single payment compound amount factor. This factor here is read: find f given p at I% interest per period for n interest periods. You may have noticed that the sequence of f and p here is the same as the sequence in this formula. This sequencing of letters is applicable for all functional symbols, and this makes them easy to remember. We can rewrite these equations in this form when performing engineering economy analysis. This is the inverse interest factor used to solve for present amount P when given the future amount F. This factor is also known as single payment present worth factor, and its functional form looks like this. How do we read this factor? This factor here is read as find P given F at I% interest factor for n interest periods. Let's recall the equations to solve for P when given F. These equations can be rewritten in this form. Again, you can see that the sequence of P and F here is the same as the sequence in these equations. We can use these factors to find economically equivalent values at different points in time. To find the values of these factors, we can refer to the interest and energy tables for discrete compounding, which was provided to you in Spectrum in PDF file. When you look at the PDF file, you will find this table, which provides us with the values of several factors, including the compound amount factors in this column and the present worth factors in this column. These factors were tabulated for various values of interest rate from 1/4% to 25% and for various compounding periods n. Now we'll try a couple of examples on how to make use of the table. $2,500 at time 0 is equivalent to how much after 6 years if the interest rate is 8% per year? We can draw a cash flow diagram as follows to analyze the problem. Here we need to calculate the future equivalent value given the present value of $2,500, the interest rate of 8%, and the number of compounding period equals to 6 years. To calculate the future equivalent value, we can make use of this formula, whereby the future value is equals to the present value multiplied by the compound amount factor. We can refer to the discrete compounding table to extract the values of the compound amount factor directly. We should select the table which is basically tabulated for interest rate equals to 8%. In searching the table, the value of the factor when n is equals to 6 is 1.5869. Substitute this compound amount factor into this formula, we get a future sum of future equivalent value F equals to $3,967. And therefore, $2,500 at time 0 is equivalent to $3,967 after 6 years if the interest rate is 8% per year. The next example, $3,000 at the end of year 7 is equivalent to how much today at time 0 if the interest rate is 6% per year? Again, it is a good practice to draw a cash flow diagram to analyze the problem. Here we need to calculate the present equivalent value given the future value of $3,000, the interest rate of 6%, and the number of compounding period of 7 years. To calculate the present equivalent value, we can make use of this formula, whereby the present value is equals to the future value multiplied by the present worth factor. Again, we can refer to the discrete compounding table to extract the value of the present worth factor directly. We should select the table which is specifically tabulated for interest rate equals to 6%. Okay, searching the present worth column, the value of the factor when n equals to 7 is 0.6651. Substitute this factor in the formula, we'll get the present equivalent value of 1,995. Okay, therefore, $3,000 at the end of year 7 is equivalent to $1,995 today at time 0 if the interest rate is 6% per year. This is a pose and solve questions. Betty will need $12,000 in 5 years to pay for a major overhaul on her tractor engine. She has found an investment that will provide a 5% return on her invested funds. How much does Betty need to invest today so that she will have her overhaul funds in 5 years? Okay, please try this question on your own first. You can either use the formula or interest table. We can discuss the answers next week. Here is the next pose and solve questions. The average price of gasoline in 2005 was $2.31 per gallon. In 1993, the average price was $1.07. What was the average annual rate of increase in the price of gasoline over this 12-year period? So you are given a hint of the formula used to solve this problem. Please try on your own. This is a questions continued from the previous pose and solve questions. In previous example, the average price of gasoline was given as $2.31 in 2005. We computed the average annual rate of increase in the price of gasoline to be I%. Okay, you should get this I% by solving pose and solve questions number 2. If we assume that the price of gasoline will continue to inflate at this rate, how long will it be before we are paying $5 per gallon? Okay, here you are given this hint to solve for these questions. Please try on your own and we shall discuss the answer for all pose and solve questions next week. Now we'll proceed to relating a uniform series or annuity to its present and future equivalent values. Okay, you will learn how to find F when given A, find P when given A, find A when given F, find A when given P, find the number of cash flows in an annuity given A, P, and I, as well as find the interest rate I given A, F, and N. Okay, A here refers to the annuity, which is also known as the annual equivalent value. Here shows a general cash flow diagram involving a series of uniform or equal receipts, each of amount A, occurring at the end of each period for n periods with interest at 1% per period. As mentioned, this uniform series is called annuity. Okay, to be noted are that P occurs one interest period before the first annuity. F occurs at the same time as the last annuity, or at n periods after P. A occurs at the end of period 1 through period n. Okay, all formulas you will see later are derived from these assumptions. There are interest factors for a uniform series of end of period cash flows. Okay, one example is shown here. If a cash flows in $8 occurs at the end of each period for n periods, and I% is the interest rate per period, the future equivalent value F at the end of n period is given by this formula, which can also be written in this form. This factor is known as a uniform series compound amount factor, and it is given by column 4 of the discrete compounding table. Let's look at one example on the calculations of future equivalent value from the annuity. How much will you have in 40 years if you save $3,000 each year and your account earns 8% interest each year? Okay, here shows the cash flow diagram. The annuity is $3,000 of saving per year, starting from the end of year 1 up to year 40. Okay, the interest rate is 8%, and you are requested to find the future equivalent value at year 40. Okay, here is the solutions. Okay, you can use this formula to calculate the future equivalent value. Okay, this is a uniform series compound amount factor, which you can retrieve its values from the discrete compounding table. Okay, looking at this table, which is tabulated specifically for interest rate equals to 8%, at n equals to 40, the value of the factor is 259.0565. Okay, you can substitute this into the formula and find the future equivalent value equals to $777,170. This is another example on annuity and future equivalent value. Future value of a college degree. A recent government study reported that a college degree is worth an extra $23,000 per year in income compared to what a high school graduate makes. If the interest rate is 6% per year and you work for 40 years, what is the future compound amount of this extra income? As usual, we can draw a cash flow diagram to visualize the problem. The viewpoint we will use to solve this problem is that of lending the $23,000 of extra annual income to a savings account or some other investment vehicle. This extra annual income is the annuity, specifically the annual deposit to the saving accounts. The future equivalent value is the amount that can be withdrawn after the 40th deposit is made. We need to find this value. Notice that the future equivalent occurs at the same time as the last deposit of the $23,000. This is the assumptions that we always make in the calculations of annuity. Again, we can use this formula to calculate the future equivalent value. We can retrieve the uniform series compound amount factor here from the discrete compounding table. At interest rate of 6% and the compounding period of 40 years, the value of the factor is 154.7620. Replacing this value in the formula, we get the future equivalent value equals to $3,559,526. Okay, this is a lot of money. That's why the bottom line is to get your college degree. Here is another example. Become a millionaire by saving $1 a day. To illustrate further the amazing effect of compound interest, we consider the credibility of this statement. If you are 20 years of age and save $1 each day for the rest of your life, you can become a millionaire. Let's assume that you live to age 80 and the annual interest rate is 10%. Examine whether the statement is true. And this is the cash flow diagram. The annuity would be $365 per year if we save $1 each day. And here we need to find the future compound amount F. To find F, we can use this formula. Okay, here is the solution. Okay, the uniform series compound amount factor can be obtained from the discrete compounding table, where the interest rate I is equals to 10% and the compounding period is 60. Okay, the value of this factor is found to be 3034.8164. Okay, putting this value into the formula, we get a future compound value of $1,107,706. Okay, thus, the statement is true for the assumption given. The moral is to start saving early and let the magic of compounding work on your behalf. To this end, we have seen how we could find a future amount from a uniform series of end-of-period cash flows. Now we'll look at how we can find the present amount instead. This is the formula and the interest factor to cater for this calculation. The interest factor here is also called the uniform series present worth factor, and we can find the values of this factor in column 5 of the discrete compounding table. Let's look at one example. How much is needed today to provide an annual amount of $50,000 each year for 20 years at 9% interest rate each year? Here shows the cash flow diagram. The annuity is $50,000 per year, starting from the end of year 1 to year 20. The interest rate is 9%, and you are requested to find the present equivalent value at year 0. You can use this formula to calculate the present equivalent value. And this uniform series present worth factor can be retrieved from the discrete compounding table, where the interest rate is 9% and the n is 20. And the value of this present worth factor is 9.1285. Substitute this into the formula, you'll find the present equivalent value equals to $456,427. This is an example on the calculations of present equivalent of an annuity. A microbrewery is considering the installations of a newly designed boiler system that burns the dried spent malt and barley grains from the brewing process. The boiler will produce processed steam that powers the majority of the brewery's energy operations, saving $450,000 per year over the boiler's expected life of 10 years. If the interest rate is 12% per year, how much money can the brewery afford to invest in the new boiler system? In the cash flow diagram, the annual cash flow is $450,000 and it continues for 10 years at 12% annual interest rate. The affordable amount P occurs 1 year before the first end-of-year cash flows of $450,000. The upper limit on what the brewery can afford to spend on the new boiler is estimated using this formula. A is the annual cash flow, and this is the factor known as uniform series present worth factor. As determined from the discrete compounding table, the value of this table is 5.6502 at interest rate of 12% and compounding period of 10 years. Substitute this factor into the formula, we can get the present equivalent value equals to $2,542,590. This is the relationship for finding the annuity A at the end of n interest periods that will be equivalent to its future value F occurring at the end of the last period. This part of the formula can be replaced by an interest factor, which is known as the uniform series sinking fund factor. In the discrete compounding table, we can find the sinking fund factor in column 6. Take a look at one example. How much would you need to set aside each year for 25 years at 10% interest to have accumulated $1 million at the end of the 25 years? We can draw a cash flow diagram like this to analyze the problem. It is clear from this cash flow diagram that we need to calculate the annuity which can generate $1 million in 25 years, considering 10% interest rate. The annuity can be computed using this formula, whereby F is $1 million and this is the sinking fund factor. By referring to the discrete compounding table, we get the value of the factor equals to 0.0102 at interest rate of 10% and 25 years of compounding period. With these informations, we'll get the annuity value equals to $10,000 $1,200. This is a relationship for finding the annuity A occurring at the end of n interest periods that will be equivalent to the present value P occurring at the beginning of the first period. This term here can be written in the form of interest factor, known as capital recovery factor. Capital recovery factor can be found in column 7 of the discrete compounding table. This is one example of calculation. If you had $500,000 today in an account earning 10% each year, how much could you withdraw each year for 25 years? Again, we can draw a cash flow diagram like this to analyze the problem. We need to calculate the annuity, which can be withdrawn from the present sum of $500,000 in the account that is earning 10% interest per year. The annuity can be estimated using this formula, whereby P is equals to $500,000, and this is the capital recovery factor. By referring to this discrete compounding table, we can get the value of the factors equals to 0.1102 at interest rate of 10% and 25 years of compounding period. With these informations, we will get the annuity value equals to $55,100. Here shows the relationship of cash flows for Plan 2 in the example on the repayment of the $17,000 loan principal. Can you apply the formula to calculate the value of annuity or the annual repayment? The annuity is easily calculated using this formula. P is the present value or the principal at 0 month, and this is the capital recovery factor at 1% interest rate and 4 compounding periods. From this table, we can extract the factor's value equals to 0.2563. Substitute this value into the formula, we will get the annuity equals to $4,357.10. Now we'll take a look at this example on computing your monthly car payment. You borrow $15,000 from your credit union to purchase a used car. The interest rate on your loan is 0.25% per month, and you'll make a total of 36 monthly payments. What is your monthly payment? The cash flow diagram here is drawn from the viewpoint of the bank. Notice that the present amount of $15,000 occurs 1 month before the first cash flow of the annuity. The amount of car payment is easily calculated using this formula, where P is $15,000, and this is the capital recovery factor, which can be retrieved from this table at interest rate of 0.25% and compounding periods of 36 months. The value of the factor is 0.0291. Substitute this value into this formula will give us an annuity value of $436.50 per month. This is another pose and solve questions. Acme Steamer purchased a new pump for $75,000. They borrow the money for the pump from their bank at an interest rate of 0.5% per month and will make a total of 24 equal monthly payments. How much will Acme's monthly payments be? Please try this question on your own, and we shall discuss about the answer next week. It can be challenging to solve for compounding period N or interest rate I. We may know P, A, and I and want to find N, or we may know P, A, and N and want to find I. These problems present special challenges that are best handled on a spreadsheet. This is an example on finding N. Acme borrowed $100,000 from a local bank, which charges them an interest rate of 7% per year. If Acme pays the bank $8,000 per year, how many years will it take to pay off the loan? This is a formula showing the relationship between P, A, I, and N. Okay, substitute P equals to $100,000, A equals to $8,000, and I equals to 7%. We can write the formula in this form. Okay, as you can see, this formula cannot be solved directly. Okay, this can be solved by using interest tables and interpolations, or using computer solution. This is an example on finding I. You invested $1,000 each year for 5 years in a local company and saw her interest after 5 years for $8,000. What annual rate of return did you earn? Okay, this is the formula showing the relationship between F, A, I, and N. In these equations, we know that F is equals to $8,000, A is equals to $1,000, and N is equals to 5 years. But we don't know the interest rate I. That makes them equivalent. When we substitute the values into this formula, we get this. And it is obvious that we can't solve for the interest rate directly. As in previous case, this can be solved using the interest tables and interpolations, or using computer solution. This illustrates the use of interpolations in interest table to solve for the desired value I or N. Okay, we can set up the non-factor values 1 and 2 and the unlisted factor value in the interest table, which we find from our calculation. A is the difference between the tabulated I or N value 1 and the desired I or N values that we are trying to estimate. B is the difference between the two tabulated I or N values. Okay, C is the difference between the two non-factor value 1 and the unlisted factor value, whereas D is the difference between the non-factor values 1 and 2. A rational equations can then be set up and solve for the desired I or N values. Okay, don't worry if you don't understand this completely. We will have a look at one example to get a sense about how this is set up and estimated. Let's take a look at one example on finding the interest rate to meet an investment goal. After years of being a poor, debt-encumbered college student, you decide that you want to pay for your dream car in cash. Not having enough money now, you decide to specifically put money away each year in a dream car fund. The car you want to buy will cost $60,000 in 8 years. You are going to put aside $6,000 each year for 8 years to save for this. At what interest rate must you invest your money to achieve your goal of having enough to purchase the car after 8 years? We can use this formula to show the desired equivalence relationship, whereby F is the future amount to buy the dream car, which is equals to $60,000. A is the annuity or the amount to put aside each year, which is equals to $6,000. And the number of compounding period is 8 years. Rearranging the formula, we get the uniform series compound amount factor for 8 compounding periods equals to 10. Now we can use the interest tables to help track down the unknown value of the interest rate I. What we are looking for are two interest rates, one with the factor value slightly less than 10, and the other one with the factor value slightly greater than 10. Okay, thumbing through the tables, we find that the factor at 6% and at compounding periods has a value of 9.8975, whereas the factors at 7% and the compounding period of 8 has a value of 10.2598. Okay, this tells us the interest rate that we are looking for is between 6% and 7% per year. Even though the function is nonlinear, we can use the linear interpolations to approximate the value of I. With the values obtained from the table, we can come up with this graph. The x-axis shows the interest rate per year, where we have 6% and 7% interest rate with their respective uniform series compound amount factors value indicated in the y-axis. Also, we have a compound amount factor value of 10, which we are trying to find the interest rate I prime. The dashed curve here is what we are linearly approximating. The answer I prime can be determined using these rational equations. Okay, line DA corresponds to I prime minus 0.06. Line ED corresponds to 10 minus 9.8975. Line BA is 0.07 minus 0.06, and line CB is 10.2598 minus 9.8975. Okay, with this equation, we can solve for I prime equals to 0.0628 or 6.28% per year. So if you can find an investment account that will earn at least 6.28% interest per year, you will have the $60,000 you need to buy your dream car in 8 years. Here shows the spreadsheet solution. Excel has another financial functions that allows you to solve for an unknown interest rate. Okay, this is the functions which accept 4 inputs. This function will return the fixed interest rate that equates an annuity of magnitude PMT that lasts for NPR period to either X present value PV or X future value FP. Okay, here is how you can write the equations in the cell of the Excel spreadsheet. We will get I prime equals to 6.29% per year. And note that a 0 was entered for the present value, since we were working with a non-future value in this example, which is $60,000. Also, because you are putting away $6,000 each year, hence the annuity is expressed as a negative number. This table gives discrete cash flow examples illustrating equivalence for the 6 most commonly used discrete compound interest factors. The formulas are for discrete compounding, which means the interest is compounded at the end of each finite period, such as a month or a year. The formulas also assume discrete cash flows spaced at the end of equal time intervals on a cash flow diagram, and the interest rate I remains constant during the n compounding periods. Please go through these examples on your own. That's the end of the lecture today. Thank you for listening. Have a good day and bye.